All right, let's jump right into it. Today, we are tackling a massive and honestly sometimes terrifying challenge that absolutely every growing engineering organization is going to face at some point: surviving the telemetry data scale-up. We're going to be unpacking Chapter 15 of Observability Engineering, focusing specifically on the mechanics of cheap and accurate enough sampling. And I've got to tell you, as we go through these concepts today, it might just completely change how you look at your entire system's data architecture. So let's get started. Let's start with a reality check, especially for all the DevOps and site reliability engineers out there who feel this particular pain every single day. Here's the big question. Can you actually afford to keep every single telemetry event your system generates? The short answer? Absolutely not. No way. When you are operating at scale, the resources necessary to retain, process, and store 100% of your telemetry data quickly become financially and computationally impossible. Think about it for a second. Your observability infrastructure simply cannot be the exact same size or cost the exact same amount of money as your actual production infrastructure. If it did, that would completely break your business model, right? As your user base grows, the everyday trickle of operational data turns into an absolute flood. And you can't just let it wash over you. You need a way to build a highly intelligent dam to manage that flow. And that dam, that structural control, is sampling. Now, I know what you might be thinking. Often, sampling is treated like a dirty word in engineering circles. A lot of folks view it as a necessary evil, a compromise where you inevitably lose visibility and start flying blind in your application. But the source text makes it incredibly clear that this is a misconception. Sampling is actually a strategic engineering hero. By definition, it's the practice of selectively deciding what data to keep and discarding the rest to optimize resources, all while maintaining data fidelity. It is absolutely not about flying blind. Actually, it's the exact opposite. It's about choosing exactly what you need to see so you can accurately understand your system's true state without paying for a mountain of redundant, useless noise. Okay, here's our roadmap for this explainer. We'll start by looking at the telemetry data flood, move into core sampling strategies, dive into the math behind reconstructing sampled data, figure out the timing of head versus tail sampling, and finally, look at automating the whole thing with target rate and dynamic sampling. Section 1. The telemetry data flood, surviving the scale-up. To survive this scale-up without completely losing our minds or bankrupting our departments, we really have to understand the true nature of the data we're emitting. Think about a healthy, functioning system. The vast, overwhelming majority of emitted events are virtually identical. They're those beautiful, successful, sub-millisecond HTTP 200 OKs. Now, storing 100% of these identical events gives you massive storage overhead with almost zero additional debugging value. If you have 10 million successful checkout events in an hour and they all followed the exact same happy path, keeping all 10 million of them doesn't teach you anything new. You're just hoarding data. On the flip side, storing a representative sample gives you a tiny fraction of the cost while perfectly preserving data fidelity. Remember, the core function of debugging isn't reading every single log line. It's searching for emergent patterns by contrasting representative good events against your bad events. You don't need a million identical success logs to spot a pattern. You just need a statistically valid baseline sample of them to compare against your errors. Section 2. Core sampling strategies, going from basic to dynamic. Let's track the evolution of sampling, starting with the most basic approach: constant probability sampling. Think of this as a flat, system-wide rule, something like keep 1 in 1,000 events. Now, it's incredibly easy to write this into your code, but it fails spectacularly under a few very common real-world conditions. First, what if you care highly about error cases over successes, which, let's be honest, almost every engineer does? Flat sampling totally drops the ball here. If a specific critical error only happens 0.1% of the time, and your flat sampling rule is only keeping 1% of your total traffic, well, the math guarantees you might completely blind yourself to a catastrophic long-tail issue. The error might vanish entirely from your observability platform because it just got unlucky and didn't get sampled. Second, consider a multi-tenant SaaS platform. Imagine you have one massive enterprise whale of a customer sending millions of requests and a tiny startup customer sending maybe 50 requests a day. Flat sampling means your dashboard will be completely dominated by the giant customer's data, leaving the startup practically unobservable. You might drop all 50 of their daily requests. And third, what happens if a sudden massive traffic surge or a DDoS attack hits? Keeping a flat percentage might still result in enough absolute volume passing through to completely knock over and crash your analytics backend. Flat sampling just isn't smart enough for the real world. To fix these glaring blind spots, we have to evolve. And we do that through sampling based on event content, which is often called key-based sampling. This is where the strategy gets really smart. Instead of a flat rule, we assign specific sampling rates dynamically based on the actual payload or attributes of the event itself. For example, your instrumentation can include logic that says, errors are so valuable that they are kept at 100%, while routine successful events are kept at a much lower rate, like maybe 1%. Or you can look at the endpoint route. Let's say newly placed orders on your e-commerce checkout page are heavily prioritized and sampled at 50%, because those directly tie to revenue, while automated background health status checks are sampled at 0.01%. You could even write a rule that prioritizes telemetry from your high-paying enterprise-tier customers over your free-tier traffic. This content-aware approach is a total game-changer. It ensures you consistently capture the most vital, high-value business contexts while ruthlessly pruning out the low-value noise.
Section 3. Reconstructing sampled data. Let's look at the math behind the magic.
Okay, so collecting the data is really only half the battle. We have to actually make sense of it once it lands in our system. Now, what's really interesting about this visual is that sample rate column on the far right. Our source material stresses a critical, non-negotiable architectural rule here. If you are dynamically changing your sample rates, you must explicitly record the sample rate inside the event payload itself. Why is this absolutely crucial? Because in a distributed system, your centralized analytics backend has absolutely no idea what the active dynamic sample rate was at the exact millisecond your edge proxy or your microservice generated that event. By passing the sample rate along as a field within the event itself, we are effectively telling our backend, hey, this single error event mathematically represents 80 similar events that we dropped at the edge. It gives the backend the context it needs to rebuild the big picture.
Let's look closely at how this actually works, using a brilliant concept from the text, the representative spokesperson metaphor. Imagine a kept event is simply a spokesperson for a group of dropped events. If we have a captured latency value of 1 millisecond with a sample rate of 5, that one spokesperson speaks for 5 ones. Now look at this data set. We've captured latency values of 1, 3, and 7. If we just naively calculate the median of 1, 3, and 7 without knowing or applying the sample rates, the median looks like 3, right? Just right there in the middle. But look at the sample rates. The value 7 has a sample rate of 9. When we reconstruct the true distribution using a weighted algorithm, expanding the data out so the 1 is repeated 5 times, the 3 is repeated twice, and the 7 is repeated 9 times, it becomes glaringly obvious that the true, mathematically accurate median of the system is actually 7. Without explicitly recording those sample rates and weighting the data upon query, your dashboard metrics, your P99 percentiles, and your SLA alerts would be completely, dangerously wrong. You'd be making business decisions on fake math.
Section 4. Head versus tail sampling. When exactly do you make the decision?
In modern distributed architectures, a single trace often spans dozens of interconnected microservices. So exactly when you make the mathematical decision to keep or drop that trace changes absolutely everything about your infrastructure. Let's contrast the two main approaches here. First, head-based sampling. This is an upfront decision made the exact moment a request enters your system, usually right at the ingress or the API gateway. Because it's upfront, it relies on static fields we know immediately, like a customer ID or an HTTP endpoint. And because the decision is immediate, it is incredibly cheap. You drop the data instantly, saving bandwidth and compute across your entire downstream stack. Conversely, we have tail-based sampling. This is a retrospective decision. It waits until the entire distributed request is completely finished, buffers all the individual service spans in memory at a collector level, and then makes a holistic decision based on dynamic fields, like whether the entire request ultimately resulted in a 500 error, or if the total round-trip latency exceeded a certain threshold. Now, tail sampling is computationally expensive and memory-intensive because of that necessary buffering period, but it is the absolute gold standard for optimizing data fidelity. It guarantees you will never accidentally drop a trace that ended up failing deep within your system.
But listen, whether you architect for head or tail sampling, there is one non-negotiable rule. You absolutely must achieve consistent sampling across your entire distributed system. The operational steps here are vital. First, generate a central trace ID upfront at the very beginning of the request. Second, propagate that trace ID downstream to every single microservice, database, and handler involved in the transaction. Third, and most importantly, keep or discard the entire trace consistently based on that single ID. The source text gives a highly relatable and honestly kind of painful anecdote about this. Imagine you configure a noisy downstream Redis cache to independently sample at 1 in 1,000, while the upstream parent checkout service independently samples at 1 in 10. If you don't use a consistent central ID to dictate the decision across both of them, you will inevitably end up keeping a broken, orphaned Redis child span while completely discarding its parent context. You'll be staring at a dashboard at 2 a.m. showing a random Redis timeout, and you'll have absolutely no idea which user, which checkout cart, or which API call actually triggered it. The trace is totally useless. You have to be consistent.
Section 5. Target rate and dynamic sampling. Automating the balance. So, to avoid waking up in a cold sweat to manually adjust sampling flags during an unexpected Black Friday traffic spike, we need to automate this balance. And this brilliantly illustrates what is essentially the holy grail of sampling. Watch what happens here. As your incoming traffic level goes through a massive, unpredictable spike, your dynamic sample probability automatically dips in inverse proportion. If traffic doubles, the keep rate automatically halves. The mathematical result of this beautiful inverse relationship is a perfectly even, steady, predictable overall sample volume hitting your observability backend. Target rate sampling continuously tracks incoming request volumes and dynamically throttles the probability in real time. This means you stay strictly within your allocated observability infrastructure budget, and your analytics database doesn't crash, literally no matter what viral event is hitting your front end. You get total financial predictability without ever sacrificing your representative visibility. So how do we actually translate this powerful target rate strategy into working code? The source provides some excellent logical breakdowns of how this is structured under the hood. First, you set up a background thread or process to track the total volume of incoming requests over a sliding window, typically looking at the previous minute. You then calculate a dynamic sample rate against a hard, predetermined target. Say, you decide you only ever want to send exactly 100 events per second to your backend. But here is the absolute genius part of the algorithm. You don't just blindly apply that rate to everything. You intelligently separate the traffic. You take anomalous outliers, like any request that took over 500 milliseconds, or any request that returned a non-200 status code, and you put them in a guaranteed tail sampling bucket. Those high-value anomalies are always kept, effectively bypassing the throttle entirely. Then you apply the aggressive dynamic rate limiting only to the remaining mundane, normal requests. This hybrid logic guarantees 100% visibility into the weird broken stuff, while dynamically throttling the boring, everyday traffic to perfectly meet your events per second budget constraint. It is incredibly elegant.
Now, I know what some of you are thinking. If tracking sliding time windows across previous minutes, continuously recalculating dynamic probabilities, and maintaining concurrent memory maps for tail buffering sounds like an absolute nightmare to code from scratch, well, take a deep breath. You don't have to. The modern observability ecosystem is well prepared for this. Existing open-source libraries and collector agents like Telemetry, often referred to as OTel, and specific packages like DynSampler Go handle all of this heavy computational lifting natively. Understanding the underlying logic we just walked through is absolutely vital so you can make the right architectural decisions, understand the cost trade-offs, and actually configure these tools correctly for your specific business needs. But rest assured, the brilliant open-source community has already written and heavily optimized the complex routing maps and memory buffers for you. You just get to reap the benefits.
Let's bring all of these concepts together. The core thesis of Chapter 15 is beautifully summarized in this overarching thought from the source. Sampling reduces the overall volume of telemetry data while maintaining data fidelity. It is not a blind compromise. It is not flying blind. It is an intelligent, mathematically sound refinement process. Mastering these trade-offs, knowing exactly when to use lightweight head sampling versus high-fidelity tail sampling, knowing how to sample dynamically by specific business keys, and understanding how to implement automated target rates, that is the absolute key to running highly observable systems at scale. It allows you to see exactly what is happening in your production environment without bankrupting your company's infrastructure budget in the process.
As we wrap up this explainer, I want to leave you with a final, provocative question to ponder with your own teams. How is your organization currently balancing telemetry fidelity with infrastructure costs? Are you brute forcing the problem by paying an absolute premium to store millions of identical, successful events that provide zero debugging value? Or are you dynamically sampling to intelligently isolate the exact emergent patterns you need to debug complex distributed issues effectively? Depending on your answer, it might just be time to take a close look at your instrumentation pipelines and put some of these dynamic strategies to work. Thank you so much for joining me today. I hope you found these engineering concepts as fascinating as I did. Keep learning, keep building, and I'll catch you next time.